general relativity, step by step. In screencast 46, I was talking about the intrinsic derivative of a vector, a contravariant vector, along a curve. And I realised I've made a mistake. If you look here, I've got a still from screencast 46. This alpha here looks like a free index. Well, it is a free index here, but it should match this one, and that's a gamma. Alpha here sums there, and the free index here is gamma. So this should be a gamma to match that gamma and this gamma, and it isn't. So it's a misleading, it's a badly formed or a malformed tensor equation. So I'm going to write that down correctly, and then I'm going to show you what I'm going to do with it. Right, I think I do that. No, this. Okay, so let's first of all write down the correct equation. I'm just going to write it down as I derived it, but corrected. D lambda equals little d v gamma by di lambda plus v alpha di x beta by di lambda, Christoffel symbol, gamma alpha beta. And I'm just going to make it absolutely clear what's going on here. So I'm going to replace that gamma with a red character just to make sure that it's free. So now it's red, red, red in the right position. And the indices that I'm summing over two indices. I'm summing over beta there, and I'm going to change to, I think I've got green, yes. Oops. That should be an alpha and an alpha. Go back to blue and make that a beta. There it is. So that's the equation that I should have written down on screencast 46. Better go back to black. Now what I'm going to do is I'm just going to make the observation that what this is, another way of writing, well actually, first of all, I've got my path here, and I'm going to define a vector field u, where u is the tangent at any point along the curve, So that's my path, starting here, index lambda equals 0, lambda equals 1, and we cruise along this path, la 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 la, and at each point we've got this tangent curve u, which is a function of lambda, I guess. Yeah, there it is. So really what I'm trying to say here is that dv gamma by d lambda, well, really what I mean to say is I mean to change d by d lambda. I should be saying dx, let's call it alpha by di lambda, d by dx alpha, where this thing is the covariant derivative. There's no good notation for that, I guess. It shouldn't be capital D's, but different people use it a different way. It's a covariant derivative. So, if I just look at this thing here, I can rewrite that slightly differently. I can say that dv gamma by d lambda equals di by alpha lambda, and then the covariant derivative of it with respect to alpha. So that equals u alpha v. Now I'm doing it again, I'm getting my alphas and my gammas. That's a gamma alpha. Yeah, that's a v. That's a v, and that's a covariant derivative. So that's quite a nice way to think about it. I'm not going to use that just for the moment. I'm just going to stick with this formulation here, and ask what I mean. I'm just going to get rid of this lot. What do I mean by a straight curve? So a straight curve, in scare quotes, because you'll remember that when I was on the surface of the sphere, we've got great circle lines, which to us look curved, but to a little insect, that's one big insect, it looks straight to him. So what do I mean by a straight curve? Well, the tangent vector doesn't change. Does not change. And you can see here I've drawn this wiggly curve here, and the tangent vector changes from point to point. Whereas if it's a straight line here, then the tangent vector is just straight. So when I ask, when I ask what field I want to add vector around the place, what I really want to do is I really want to take this formula here, but the vector field I want to change is u, the tangent field. And I want to make the point that as I move along lambda, the total derivative of u does not change. So I've got a v there, I'm going to substitute that for u. It's a little bit cheeky, but I'm going to do it anyway. Let's just get rid of this lot here, and I'll write down what I've got. What I want is, along the curve of u, du gamma by d lambda has got to equal 0. So let me use this formula here and just expand that a little bit. So what that means is that u alpha, you see it's a v here, but I'm substituting v equals u. What have I got? Gamma total derivative alpha, sorry, that's covariant derivative, equals 0. Covariant derivative. So that's a nice way of thinking about it, but all I'm going to do is to evaluate that in slightly different notation and show you what it means. So I'm going to start with this equation here, and I'm just going to redefine that one. So let's just try that. So let me just write it out for a start. Du gamma by d lambda, which is this one here, equals du gamma by d lambda plus, all I'm doing is writing out this equation here, but with u in place of v. And I guess I'm not doing the colours either. Oh, for goodness sake, that keeps on happening. Don't be nuts. Plus u alpha from there, di x beta by di lambda, alpha beta, just copying that equation there. And this thing equals 0. So now I'll make the observation or remind myself that u with any index, call it delta, is just di x delta by di lambda. And so I'm just going to use that in here. So that tells me that d by d lambda of, actually these are straight, dx gamma by d lambda plus this term here, dx alpha by d lambda, for that term there. This one doesn't change. dx beta, I might have written a curly one rather than a straight one, down beta, Christoffel symbol, alpha beta equals 0. So that tells me that d2x gamma by d lambda plus dx alpha by d lambda dx beta by d lambda alpha beta equals 0. And that is my geodesic equation. Or one of them, there's other ones I can use. Geodesic equation. Equals definition of a straight line. Straight in scare quotes. What it means is as straight as possible. In your surface. Okay. Actually, I so like the discipline of writing the indices in different colours. That's red, and that's red. So that one's the free one. And what are we summing over? We're going to sum over alpha, which is there, and beta, which I got rid of by mistake, is there in green and there in green. So the only free indices left are red ones, the gamma. And this is my beautiful definition for a geodesic equation, which is really rather nice. And it works in any curvilinear coordinate system. It works in curved spaces. It means that the tangent vector u, in green. It means that the tangent vector u is constant along the curve. That's what it means. it means that u is constant along the curve, so it means that the curve must be straight. And that's the tangent. That's the tangent. So if we've got this curve that's parameterized with a tangent vector u, we're specifying that that tangent vector doesn't change as we cruise along that curve. So this is the geodesic equation. Geodesic equation. Beautiful thing. So there we are. I'm going to fool around with that. It's absolutely beautiful. Stop.